In this video, we want to look at how to invert a 2x2 matrix, a square matrix. So let's start with our matrix A, which is 2x2. And let's suppose the elements are 2, 1, 4, and 3. And as you may recall, the formula for the inverse of A, it's equal to 1 over the determinant of A times the adjoint of A, where the adjoint of A is simply the transpose of the cofactor matrix. And if we look at this formula, you'll quickly see that if the determinant of A is 0, then the inverse of A is undefined or does not exist. So the first thing I would suggest that you do when trying to find the inverse of a square matrix is to find the determinant of A first. And if it is 0, the inverse will not exist. So for our matrix A, let's look at the determinant of A, which again is the difference between the cross products. So it's 2 times 3, which is 6, minus 4 times 1, which is 4, which is equal to 2, which is not equal to 0. So we know the following results. We know that the rows and the columns of A are linearly independent. We know that A is a non-singular matrix, and we know that the inverse of A does exist. So what's the next step we need to look at in finding the inverse of A? Well, we already have the determinant of A, so now we need to find the adjoint of A, which is the transpose of the cofactor matrix. So first of all, let's get the cofactor matrix, and then we can find the transpose of it. So the cofactor matrix of our A matrix is found by replacing every element of the A matrix with its cofactor. So we know that A is 2 by 2, so the cofactor matrix of A will also be 2 by 2, 2 rows and 2 columns. Okay, let's get this first element in the cofactor matrix. We're looking at, remember the elements of the A matrix are A11, A12, A21, and A22. So how do we find the cofactor of this first element in the A matrix, the cofactor of element A11? We first of all need to find the minor of element A11. To find the minor of this element, we look at the subdeterminant of A, formed after deleting the row and column containing that element. So the subdeterminant of A we're left with is the determinant of 3, and the determinant of a scalar or the determinant of a number is just the number itself. So it's the number 3 is the minor of element A11. But we need the cofactor of element A11, not just the minor. The cofactor of element A11 is the minor of element A11 with an appropriate sign. How do we find the appropriate sign? Well, since we're looking at the element A11 and its cofactor, we look at those two subscripts of A, A11. 1 plus 1 is 2, which is even. So we put a plus sign there, attach that to the minor of element A11. And this gives us the cofactor of element A11, which is just plus 3. Let's get the cofactor of element A12. How do we find it? We first of all have to get the minor of element A12, which again is the subdeterminant of A formed after deleting the first row and the second column, which is just the determinant of 4, which is 4. And then to get the cofactor of element A12, we need to attach a sign to the minor of element A12. Well, since 1 plus 2 is 3, which is odd, the sign is negative, so we attach a negative sign to the minor of element A12, and that gives us the cofactor of element A12, which is minus 4. Similarly, we can find the cofactor of element A21 as the minor of element A21, which is the determinant of 1, which is 1. To get the cofactor of element A21, 2 plus 1 is 3, which is odd, so we need a negative sign attached to that minor of element A21, and then the cofactor of element A21 is just minus 1. Finally, the cofactor of element A22 is the minor of that element, which is 2. The cofactor of element A22, 2 plus 2 is 4, which is even, so we put a plus sign to that, and that gives us our cofactor matrix. Now to find the transpose of the cofactor matrix, which is also called the adjoint of A, or the A matrix, we simply transpose the cofactor matrix. How do we do that? The first row of the cofactor matrix becomes the first column of the transpose of the cofactor matrix, and the second row becomes the second column, -1 and 2, and that gives us the transpose of the cofactor matrix, or the adjoint of A. Okay, now we're ready to find the inverse of A. The inverse of A, according to our formula up here, is simply equal to 1 over the determinant of A, which is 2, times the adjoint of A, or the transpose of the cofactor matrix of A, which is 3 minus 1 minus 4 and 2. And now we just have to perform scalar multiplication of a matrix. The matrix times a scalar, you just take every element in the matrix and multiply it by that scalar or number 1/2. So the results become 3/2 minus 1/2 minus 4 over 2, which is minus 2, and 2 times 1/2, which is 1. So the inverse of A, that minus the inverse of A, is simply equal to this matrix right here. That's the inverse of A, or the inverse matrix of A. And you should always check your answer. So how do we know that this matrix here is truly the inverse matrix of our A matrix? Well, the property of the inverse matrix is that if we take the A matrix and multiply it by its inverse matrix, we should get back the identity matrix. And let's see if we get that. I'm going to rewrite the A matrix 2, 1, 4, 3, and I'm going to post-multiply that by our suspected inverse matrix of A, or the inverse of A, minus 2 and 1, and let's see if we indeed get back a 2 by 2 identity matrix. 2 by 2 times a 2 by 2 will give us a 2 by 2 matrix. Okay, the element in the first row, first column, how do we find it? First row lead matrix, first column lag matrix, 2 times 3/2, which is 3, plus a minus 2, which is 1. First row, second column of the product matrix, we take the first row of the lead matrix, first column of the lag matrix. 2 times a minus 1/2 is a minus 1, plus 1 times 1 is 1, which is 0. Second row, first column, how do we find it? Second row lead matrix, first column lag matrix, 4 times 3/2, which is 6, plus a minus 6, which is 0. Second row, second column, 4 times a minus 1/2 is a minus 2, plus 3, which is 1. And that does, in fact, verify for us that our inverse matrix of A that we derived is correct.